Okay, so today we're going to learn about the activity series of the elements, which is a tool that you can use to predict whether or not a reaction will take place. So our goal simply by the end of the day is just that you'll be able to take a reaction that I give you, use the activity series, and tell me whether or not you think that reaction would actually occur. We describe an element's ability to react with something as its activity. So if something reacts really easily, really readily with stuff, then we would say that it is high activity. And if something doesn't react quickly, takes a long time to react, is very difficult to react, or simply doesn't react with things, we would call it very low activity. An activity series is very simply a list of elements organized according to the ease with which the elements undergo certain chemical reactions. So they've just put together a list based on activity. They usually put the very reactive or high activity elements at the top and the low activity ones at the bottom of the list. For metals, the greater their activity is, the easier it is for them to lose electrons and form positive ions. And for nonmetals, the greater their activity is, the easier it is for them to gain electrons and to form negative ions. So to use an activity series, okay, they're usually created based on a single displacement reaction, okay? And what I mean by that is they're looking at, would this thing replace the other thing in a single replacement reaction, okay? So the most active element is placed at the top of the list, and it would replace any of the elements below it on the list in a single replacement reaction because it's very active. Elements that are farther down in the series could replace anything that's underneath them, but they can't replace anything that's above them. If you'll remember when we talked about the halogens, we talked about how a halogen that is at the top of its group can replace ones below it. That's basically the activity series for halogens by themselves, okay? So we're going to do a similar thing. If you look at the activity series that's in that green chart at the bottom of your notes, then the element that's at the top could replace anything underneath, but then as you go further down, they can replace what's under them, but not what's above them. An activity series can be used then to help predict whether or not a reaction is likely to occur. Give folks a sec to write. Let's look at an example of this, okay? According to our activity series, aluminum would be able to displace zinc, because if you look at that list, you'll see aluminum is above zinc. So we would predict that this reaction, 2 aluminum plus 3 zinc chloride, would yield 3 zinc plus 2 aluminum chloride. So we're predicting that this reaction would take place because aluminum is more reactive than zinc. So when they were dissolved in solution, the aluminum would go in and displace the chlorine or displace the zinc and bond with the chlorine instead, and we'd yield aluminum chloride and then solid zinc by itself. However, on the flip side of things, cobalt is lower on the table than sodium. So cobalt would be unable to displace sodium. So if somebody wrote for you the reaction cobalt plus sodium chloride, you would write the latter half of the reaction simply as no reaction, because we are predicting that this reaction would not take place because sodium is going to be more likely to bond with that chlorine. It's more active, and so the cobalt would be unable to displace it. You to remember and keep in mind that like other useful tools in chemistry, the activity series is based on experimentation. So this isn't just a group of people who sat down and they were like, well, I think sodium is more likely to bond than cobalt. No, they actually went out and ran tests and discovered in which in which situations things reacted. And based on those tests, they were able to identify which ones were very reactive and which ones were not. So it's a very useful tool, but it is just based on experimentation that we have this tool at our disposal. So I'm going to start by just doing an example not from the homework for you, that I will just show you how I would run it, and then you guys will do one together from the homework, and then you can work on some on your own. So we are going to look at number 2 here, because the first one is just a conceptual question for you to answer. So they want to know, based on the activity series, to predict whether each of the following possible reactions will occur. The one we're going to start with is from some sample problems in your book. So we're going to see if zinc in its solid form will react with water in its liquid form. Oh, I wrote that sloppy. There we go. In its liquid form. And they're saying it is at 50 degrees Celsius. Okay, and then they want to know, is this reaction going to form? And if it will go through, what will the products be? So we're going to look at that activity series that's on page 278 of your books or in your notes. Okay, and we're going to look at zinc. Zinc is in that second section from the top, where it says they will react with steam, but not with cold water, and with acids replacing hydrogen, and they will react with oxygen, forming oxides. So they say it will react with water, but only if that water is in the form of steam. It won't react with cold water. So we're saying in this reaction that it's in its liquid state, and that it's at 50 degrees Celsius. Okay, 100 degrees Celsius is boiling. So at this point, is this water steam? No. So will this reaction take place? No. So we would just simply write no reaction. Okay. So I'm going to just wipe the screen. Now we're going to do one from your homework. So we're going to do letter A, where it says nickel in its solid state reacting with H2O in its liquid state. Will that reaction take place? So you go ahead and take a look, and then we'll walk through it together. So because these activity series are modeled on single replacement reactions, usually the one that you are going to look at first is going to be whichever is first in your thing, because it's solitary by itself. So it's going to be the one that we're assuming is doing the replacing, and then we can look at what it might replace. Okay, so to begin with, we're going to look at nickel. We're going to find nickel on the activity series. It's actually in the third box from the top, where it says does not react with water, will react with acids, will replace the hydrogen in the acid, and will react with oxygen to form an oxide. Okay? So the rest of that information would be useful for us if we were trying to predict what was being created, but since we're not trying to predict what's being created yet, we're just going to see if it will react, and the answer to that question is no, it's not going to react, because we read that very first sentence says does not react with water, which means that even if the water happened to be in its steam form, which we don't have indicated, it still would not react. Nickel just simply doesn't react with water. So we would again write no reaction here. Shall we do another? Okay, I'm going to go back to my sample problems from the book. Let's do tin in its solid form plus oxygen in its gas form. So go ahead and try to determine, first off, just try to determine if this reaction will occur or not. Think. Yes, it is going to react with oxygen. We can see there it says that tin reacts with oxygen, forming an oxide. So we're going to wind up with tin oxide as our final product here. Okay. So we should end up with either SNO or with SNO2, because if you look at tin, you'll discover that tin has more than one charge that it can form, so it's possible that we'll wind up with different oxides. Okay? So in the case where they're asking you to predict the products, you would want to list all possible products. So if the metal has the ability to form more than one oxide, you want to list all of them that it could form. Sound good? Okay, let's do one from your homework. I'm going to go ahead and erase this. We'll just do the next one down. We'll do letter B, which is bromine in its liquid form plus, looks like potassium iodide, dissolved, aqueous. Go ahead and take a look. Try to determine, will this reaction take place, and then we'll do the next part. Yes, this reaction is going to take place, okay? So in the previous reaction, we were looking at tin and oxygen, which was a synthesis reaction, right? 1 + 1 yields a compound. In this case, we have a substance and a compound. So what we're likely looking at here is a displacement reaction. So what we need to determine is, will bromine displace the potassium? Or are we thinking, will it displace, I think it'll displace the iodine. Yeah, duh, because bromine is also a halogen, so it's gonna replace like. So the bromine, will it replace the iodine? If we look at the activity series, we see that bromine is more reactive than iodine, which means it will replace it, and we would wind up with potassium bromide, and in its aqueous form, so it would stay dissolved, and then we would get solid iodine coming out of it. And we know that we must have iodine because we have to balance this equation, right? So my process of elimination here is, we've got a solo substance plus a compound, which, like we said, likely means replacement reaction, right? Where one thing is replacing the other. This is a, right here, this is a ionic compound between potassium and iodine, okay? A metal and a nonmetal. And the iodine is a halogen, okay? It wouldn't make sense for the bromine to come in and replace the potassium because bromine doesn't form positive ions. It's going to form a negative ion, and it's going to form a negative ion equivalent to the iodine that's already in the compound. So that's how I determined that the bromine is going to replace iodine. And we know that it can replace iodine because iodine is lower than it on the activity series. So bromine is more reactive, which means it would bump it out of place, okay? And then we know that there must be iodine by itself left over because that is how displacement reactions work, right? We don't destroy the iodine, we just remove it from the compound. And then I know that iodine is a diatomic molecule, so I put a 2 under there, and then I would have to balance the equation by putting a 2 here if I was balancing the whole equation, actually. But that is how I know. And then in terms of determining what state it's going to be in, we have a bromine in its room temperature state is a liquid. Solo iodine in its room temperature state is a solid. So we assume that it will be a solid. So there is a little bit of information that you might have to go digging for, okay? I'm not going to knock you in terms of, oh, you didn't put the right state on there, because that's a lot of new information for you. Mostly I'm curious that you know, okay, this replaces this, and then because it replaces this, this is on its own now. You can think about it like somebody comes up and wants to steal you from a dance, right? The bromine is just much more suave than the iodine and comes up and is like, can I butt in? And shoves the iodine out of the way and forms a bond with the potassium, and then iodine's left to go dance by themselves for a while.
So if there's a reaction
Okay, I'm going to give you some time now to work on the homework in class so I can help you if you get stuck. If everybody seems to be stuck on a similar problem, we'll run it on the board, but otherwise we'll just have some work time.